Welcome back to Algebra 1 with Miss Betsy. In this video today we are going to be concluding our chapter in which we were beginning to learn how to factor polynomials. We learned about factoring out a greatest common monomial factor. We learned to recognize and factor the difference of two squares. We learned to recognize and factor perfect square trinomials. And we've begun to accumulate some practice in factoring trinomials that don't fit any special case. There's no neat little formula that they have that you can immediately recognize. Factor those trinomials, but what we've seen is that there is really some trial and error involved in factoring a lot of trinomials, and that the more practice you have in this process, the easier it is to factor the polynomials. What we're going to do in this section is pull all of those skills together, the different little pieces of the puzzle that we've been learning in the last few videos, to make sure that we're able to do what they call factoring completely. Now we're in Algebra 1, we're not in Algebra 2, obviously, so we're going to put a limit over what we do when we factor. It is true that every polynomial can be factored. It is not true that you can easily factor every polynomial in the method that we've been using. So we're going to limit our definition of factoring completely to say that we're going to factor this completely over the set of integers. And for those of you who are just getting into Algebra 1 right now, that may not make a whole lot of sense to you. That's okay, but all I need for you to understand at this point is that we're going to put a limit onto how we can factor something. And if we cannot factor that polynomial over the integers, we're going to say that it can't be factored. Okay? Before we go ahead and get started with our examples for today, can you tell me why it is that you just are not able to play basketball with a herd of pigs? Well, you can't do that because they have this really annoying tendency just to hog the ball. If you're tracking with me, I'm using as my text Algebra 1 for Christian Schools. It's the second edition of this book, and it's published by Bob Jones University Press. I'm in section 9.7 on page 386. It's called Factoring Completely. So let's dive right into this. And our instructions simply say factor. So we are going to factor the binomial expression 5ax to the fifth ax to the fifth minus 5 ax y to the fourth. Look at this expression here, 5ax to the fifth minus 5ax y to the fourth. And you first think, my goodness, that's a mouthful of letters and exponents. What in the world am I going to do with this? If you'll remember, what's the very first thing that you want to do when you factor a polynomial? First, you're going to look for a common monomial factor. It's like looking for the greatest common factor between, like, the numbers 16 and 24 and 60. When we talk about a monomial factor, we mean there's just one term in that factor. But we're also going to be having variables. There can be a variable that's a part of that factor. So we look at this binomial expression here, and what do we immediately see that we have in common? Well, we see there's a factor of 5 in each term. We also have a factor of a in each term. We have one factor of x and a factor of x here. So there's quite a lot of factors here we have in common. We're going to take factor every one of those out. We have 5ax. Then we're going to have our remaining binomial. What do we have left? If we factor 5ax out of 5a x to the 5th. We have x to the 4th. Then we factor 5ax out of 5axy to the 4th. Clearly we only have y to the 4th remaining. Let me show you right quickly. If you don't see what you can factor out, what we're actually doing is we're saying 5ax to the 5th and dividing that by 5ax. You see that we have a common factor of 5 that cancels. We have a common factor of a that cancels. And we use our exponent rules to tell us when we have x to the 5th divided by x, all we're going to do is subtract those exponents. So it becomes x to the 5 minus 1, which gives me x to the 4th. And you should be learning to automatically check yourself when you factor expressions. Okay, I've written this. My next thought in my head is going to be, let me distribute back and make sure that I've done this correctly. What is 5ax times x to the 4th? It's 5ax times x to the 4th. We add the exponents, gives us my 5ax to the 5th. Obviously 5ax times the negative y to the 4th gives us the negative 5axy to the 4th. Okay, now we look at this and we think, nothing that I can do here. This sort of looks like the difference of two squares, one of our first special cases that we considered as we began this chapter, but you've been used to thinking of maybe something that looked like x squared minus y squared. And you had learned that this was clearly what they call the difference of two squares. Two squares that we're subtracting. And you learned that you factor this into the sum of the square roots of the terms times a second factor that was the difference of the square roots of the terms. But we've got something strange going on here. We don't have x squared or y squared, we have x to the 4th. But x to the 4th is a perfect square, isn't it? And you're saying, how can it be a perfect square? X to the 4th is also written as x squared squared. Y to the 4th can also be written as y squared squared. So what we have here is the need to recognize that x to the 4th minus y to the 4th is in fact the difference of two squares. So once we have recognized this, we can factor our difference of two squares. X squared plus y squared, x squared minus y squared. Do you see what we did here? Listen to the vocabulary that I said, that I used. When we have the difference of two squares, x to the 4th minus y to the 4th, that factors into two binomials. Here we have two binomials. The first binomial factor is the sum of the square roots of the terms. The second factor is the difference of the square roots of the terms in that binomial. Right here I showed you how x to the 4th can be expressed as x squared, all of that expression taken to the second power, which also means that the square root of x squared squared is equal to x squared. A lot of x squareds in there, and I'm sort of beating a dead horse here, but I'm just trying to get you to make sure that you understand what we're stepping through here. Now, we have gotten to the point where we have completed our first step of factoring here. We took out a common monomial factor. Greatest common monomial factor was 5ax. Then we recognized that we have the difference of two squares. So we factored this according to the formula that we learned to use for the difference of two squares. And it would be very easy to fall into the trap of saying, yes, I'm done. You're not done. Nope, not finished yet. Well, why not? 5ax times the quantity x squared plus y squared. This is the sum of two squares, and you cannot factor that. However, look at this third expression over here. We have x squared minus y squared. What you have again is another difference of two squares. So the completely factored form going to be 5ax times the quantity x squared plus y squared times x plus y times x minus y. Now we are completed, and in this particular problem we had to factor 3 times. First we factored out a common monomial factor of 5ax. First thing. Second thing was that we recognized that x to the fourth minus y to the fourth is the difference of two squares, so we factored that. And then we looked again and we thought, oh my, I have another difference of two squares, and we factored that. Greatest common monomial factor first, difference of two squares once, difference of two squares a second time, and that's what you're going to find a lot when you are working with factoring in Algebra 1. So let's go ahead and look at a different type of example. And this is where sometimes a polynomial can have a common binomial factor in there. Let me illustrate what I'm talking about. Say that we have this expression here, 3 times the quantity x plus y minus y times the quantity x plus y. And you look at this thing, looks a little bit messy, doesn't it? Well, remember, factors are those things that you multiply together to end up with a product. We have a factor of 3 times this entire factor, x plus y, and we lump that together as a factor because it's included in parentheses. Means that it's traveling together. So when you remember that items, the quantities within parentheses, are treated as a single item, you see that we've got a common factor here of x plus y. So what we want to do is remove that common x plus y factor, x plus y, and it's essential that you keep the parentheses around this factor, because without those parentheses, you're going to have a completely different problem. I'll go ahead and illustrate that in a moment for you. When we remove a factor of x plus y, what do we have remaining? We remove x plus y, we have 3 minus y. So we factored our problem. X plus y times 3 minus y. Okay? Now what would happen if we didn't have the parentheses around here? Let me just step you through this exercise. What we have here are two binomials that we're going to multiply together. We'll use 4. First term, 3x. Outside, minus xy. Inside, 3y. Outside, minus y squared. Okay? we have 3 times x plus 3 times y minus xy minus y squared. Okay, so we factored this properly. Now watch what happens if we change our problem, if we get careless or if we think we don't have to have those parentheses, and we change this into x plus y times the quantity 3 minus y. We're no longer multiplying two binomials together. We simply have this y that we're distributing. So we have x plus y times 3 is 3y minus y times y, which is y squared. So you see that our problem is completely different. Make sure that you do not fail to include the parentheses to indicate what exactly you're using as a factor. Okay, this still may look a little bit strange to you. Let me back out of this and show you a different way to consider what we've done. How about if we said, we're going to just do a little bit of substituting on our own here, and we're going to say, let z equal the quantity x plus y. If z is going to represent that entire expression, x plus y, then couldn't we say 3 times z minus y times z? Reasonable? All we've done is we've said that z and the quantity x plus y is has the same value. So every place I have x plus y, I'm going to substitute a z. And now it just jumps out to you as being very obvious. Well, yeah, of course, I have a common factor of z. I have z times 3 minus y. What is z equal to? Z is equal to x plus y. If this is messing with your brain a little bit, sit back and ponder what we've done, rewind the video, and this technique here where it's called factoring out a common binomial. We've dealt with common monomials. Now we have a common binomial factor that we're looking for. New tool to add to your arsenal of weapons, I guess, for defeating these problems. Let's go ahead and do one more example. This one is a little bit stranger still. It's really not hard. It's just that you need to become accustomed to looking for these different cases, different things that you're using when you're factoring. We have factor the quantity a times m minus a times n. We're subtracting p times m minus p times n. See how we really have a whole lot of alphabet soup going on. Check your problem, make sure you've copied it correctly. an minus the quantity, pm minus pn. Now we're going to look here and say, okay, what do I have in common? Let's look here in this first binomial. I have an a in common. So I'll factor the a times, what do I have remaining when I factor out the a? I have a factor of m minus n. That's what I have remaining when I've removed a common monomial factor. Let me write myself a little note here so that you see what we did. We have a common monomial monomial. It's hard to write monomial and talk at the same time. We're pulling out a common monomial factor here of a. Do we have a second one? I'll bet we do. Minus pm. Pm, what's our common monomial factor here in the second portion of the problem? So p minus p. I have a remaining inside this parentheses, I have m minus n. M minus n, m minus n. This is what we've just been talking about. We now have a common binomial factor. And what is that binomial factor that we have in common? Well, yeah, of course, this entire expression. So now we have quantity m minus n. What do I have remaining when I factor this out? I've pulled out a factor of m minus n. I have an a remaining. I pull out that factor of m minus n remaining again, have a minus p. This expression right here, m minus n times the quantity a minus p, is the factored form of this puppy up here. Okay? We've found a common monomial factor to remove. We have found a common binomial factor to remove. Now, we're finished. We don't have a difference of two squares. We don't have perfect square trinomials. We don't have a trinomial that we need to factor by trial and error or factor by inspection. So we have completely factored this problem. Okay? One last one that I'd like to do. Should be something that's pretty straightforward for you, once you consider it just for a moment. We have x to the fourth minus, let me rewrite that, we have x to the fourth minus 9x squared plus 8. Okay? Obviously not the difference of two squares. It's not a perfect square trinomial. You remember that a perfect square trinomial, the first term and the last term both have to be perfect squares. 4 plus 4 is 8, but 8 is not a perfect square. So we're going to have to factor this polynomial by trial and error. The first term, x to the fourth, is a perfect square. So we have x squared. Now, in order to come up with our second terms in each of these binomial factors, we're going to have to factor the 8 so that we have, when you multiply those factors together, you have a positive 8. You add them and you get a negative 9 as the sum. The only way you can have a positive product and a negative sum is if both those factors are negative. So we have x squared minus, we have x squared minus again. How can we factor 8? There are two different ways. We can say 1 times 8. We can say 2 times 4. Obviously, if we need a sum of a negative 9, our factors are going to be a 1 and an 8. So we have x squared minus 1. We have x squared minus 8. Are we finished yet? Well, it looks like we might have the difference of two squares. Sure enough, we do. X squared minus 1 is a perfect square. X plus 1, x minus 1, x squared minus 8. Can we do anything with this x squared minus 8? No, we can't. It's the difference of 1 square, but the 8 is not a perfect square, so there's nothing further we can do. This polynomial has now been factored completely. Go ahead and work with these. I promise you, the more effort, the more time, the more practice that you put into learning how to factor polynomials, the easier it'll become. It will become enjoyable, but it's also foundational. You're not going to be able to do well as you progress through your high school math or your college math until you conquer this challenge of factoring trinomials. So hang in there, text me if you need help, and I'll see you next time.